Okay, so I did have a couple announcement sort of things that should have made it on my white paper tonight that I forgot about. One of those is now that we're migrating back towards campus, there is a computer club here at Sellersburg IT, Sellersburg branch of the School of IT, SLIT, is where I see it written down. And we're hoping to get this going again. So a meeting on November 4th, that's gonna be this Thursday. In Ogle 162, that's the secure lab right around the corner. And you'll notice there's a Zoom call on there. This flyer's in an announcement. There's a number of reasons to join clubs. They look good on resumes. Active participation, we do some fun stuff. Some of you are all around Sellersburg might remember a couple years ago before everything shut down for COVID when Ed did the Christmas tree thing, the club project for the fancy Christmas tree that sat there by the fireplace in Ogle Hall that played music and all that stuff, decorated with old computer parts. So fun stuff like that. The computer club here in the past, we've regularly had LAN parties. If there's any gamers, usually on a Friday afternoon. Commandeer one of the many empty classrooms on Friday afternoon. Use the big whiteboard and projectors and play games, but it usually ended up being Smash Brothers. I just don't want to say specifically Smash Brothers. There was always alternatives. It just always ended up being Smash Brothers. And pizza and wings and that sort of thing. So we're hoping to get that stuff going again now that we're back on campus. The mask might be an issue for the LAN party, but if you find that interesting, join that meeting either through Zoom or show up here on campus. And it is kind of nice to be around people again after a year and a half at home, and kind of weigh in on that, on where that stuff goes. And it's good to be active and other stuff. So basically there's the computer clubs. We're gonna have a general interest meeting on Thursday in the secure lab. So it'll be unlocked, or Thursday at 5:30. That's my office hours, so I'll be in my office at that time and I have a key to it if you get here early or something. The other thing is, I know everybody's at different levels in this course. Right? Some of y'all have maybe had a bunch of programming in high school or just picked it up along the way through life. Different reasons. Maybe you've seen a lot of programming. Maybe you've seen a lot of Python before. I know some people have. I knew that going in, and then there was one that just on that first week's homework, it just stood out as exceptional. She went above and beyond and did some really, really nice things in the code. I was like, oh yeah, I knew she had from previous classes. Like, I knew about the previous experience in Python. And that's the situation I was in when I returned to school. There's a lot of things that I knew because I just have a general interest in learning. I find it interesting, all the things that humanity knows and has the accumulative knowledge of humanity after all the eons of writing and storing our knowledge. So I spent a lot of time learning, but I didn't have any paperwork to prove that I knew that stuff. And oftentimes that's a requirement for a job, just to get your foot in the door, or just to get in there and talk to them and prove that you have the skills. Then we see that paperwork. So there were a whole lot of classes that I sat through where what I knew before taking that class, the class wouldn't even get as far as what I already knew, which left me bored out of my mind in quite a few things. So if you've had some Python before, after I saw that on the first week assignments and remembered that, I did go ahead and try to make an adjustment for that so that those who are already familiar with Python, or maybe those who just like a challenge, because some of us just like facing a challenge. I'm going to start putting slightly more complicated homework assignments in there. I have ideas for a couple of sections. So far, it's in the module 2 one. I think it was 2. On the textbook assignments are the textbook assignments. Those should be, if you have Python experience, that should be just easy going through the motions. Otherwise, it'd be kind of getting started. But for those who've had a lot of experience with Python, maybe it's something more challenging to do. So with the actual programming assignment ones, added some slightly more difficult questions. Also on this one, I put in this little fact. They started talking about mixing colors like we learned about in elementary school. So I kind of put in a correction on those facts, because you probably heard that way back in elementary school, you learned red, yellow, blue, and now as a computer person, you hear red, green, blue all the time. And it seems a discrepancy. It's different things. So I kind of wrote up what that's about. A quick version of it, just to get the facts straight. And I didn't write the assignments. I used the statewide course shell. So for one, mixing the red, yellow, blue, that's reflected light. So when light from the bulb bounces off something and bounces off my shirt and then makes it back to my eyes, that's the red, yellow, blue mix. And it's actually magenta, yellow, and cyan. Just we learned that we teach that to little kids and have for many, many centuries. That's been the standard art lesson for little kids that probably don't know the words or the specifics that come with words like magenta and cyan, but they probably know what red and blue is. Whereas source light, things like pixels on a screen, where we're actually looking at the source, that's a mix of red, green, and blue. And I would think the red, green, and blue are a little more relevant to computer people, but I didn't put the assignment together. The assignment is just check that. And then for people who have had Python before, I don't have any ideas. Basically, I went through and took pictures of a more advanced Python book. Oh, there's no level 2 ones. So basically, like, go through these chapters from a more advanced book. I just opened the same one again. Let's try this one. Okay. Yeah, and answer like a level 2 or level 3 question. So that instead of just a simple if statement, if you've had some Python before and would like more of a challenge, write a program about calculating perfect numbers, level 2 one there. Or a level 3 one, write a rock, paper, scissors game. Yeah, that bothers me every time I see that in that book. They wrote that wrong. The game's called rock, paper, scissors, not scissors, paper, rock. It's just like, it shouldn't bother me as much as that does. It's like, but that's there if it applies to you, because I don't know everybody's background. And I was reminded by that of somebody that I knew has had Python before. And when I saw the first week's homework assignment, I was like, oh yeah, she writes really, really good code like that. She's gonna be bored out of her mind in this class. So that'll be there in a couple weeks. I have some ideas for a couple of the modules, but if I don't have an idea, I'll just take a picture from that. And if you've had Python before, that way you might hopefully work in problems closer to your level, not necessarily introduction level when you don't need to work the introduction levels. Right? We're in a classroom, we can still try to challenge ourselves and reach for that improvement. That being said, sometimes easy A's are nice. There's some people that are in that situation that have had Python before, choose to take this class at a time when they have really hard other classes, because, well, if you're familiar with Python, then this class will kind of come out as an easy A. But that is there if you want it. And the instructions are there, and they'll be on all of the programming assignments from here on out. The textbook assignments, those are from an introduction to Python textbook programming thing. So it's going to be intro level on all of those. So hopefully not too bad, but hopefully that'll give some of y'all a good challenge instead of a good way to challenge yourself and improve your Python coding skills. Which we can look at a couple other things here. So we're talking about the selection structures. So I'll come back over to the PC, Windows, and share my screen here, which I also forgot I can zoom in on PowerShell. Control scroll, maybe make that a little bit easier to read. So we saw before the break and talked about that some, that we can, it doesn't have to be comparisons per se. We don't have to say, check and see if X is smaller than another number. We can just check if X is 0 or not 0. Oftentimes that will apply, be applicable for us. Those comparisons, though, those return true or false. So here, again, trivially assigning it, though when this situation shows up in an application, there would probably be a whole bunch of things that led up to eventually having a true in that variable. Hopefully that makes sense, right? All the stuff that happens above that's abbreviated out of a trivial example, so we can just look at the point directly. So not necessarily a trivial assignment like this, but after a whole bunch of steps through a program, we'll have either a true or false directly stored somewhere. And then we can just check that if we have that. It makes the code look a lot nicer. Because that one, it's almost pointless to run it, but I will anyway. Obviously, true returns true, false returns false. This work in Python? Nope, that's an error. Most of our languages, we can just say like not, use that for a not. But Python, we have to actually type that. So we can say not what's stored in X as well. And not false, obviously being true. We can check other things. So let's put it on my short list here. Is numeric. That's a very useful one because we'll get some input. Right? This time I'll do it from input. Give me a number. Because when we do this, well, the input, this is just our default standard input. That is coming from a keyboard. The keyboard's Unicode. That's going to be a string. That's coming in as a string, even if somebody types 432 to enter 432. It's coming in as a string. And instead of casting it directly, we might want to know if that's a number before we cast it. So we can check that with this built-in method. It goes with strings, so it's actually part of the next module. But once we have something stored in X, a thing about Python is only object-oriented programming. We do not have primitive data. Right? So you might remember back in your SDEV 120 class, they would have said things like 0, 0, 1, 0, 1, 1, 0, 1 is a what? 32, 40, 44, 45. So that represents a 45. That is raw primitive integer data. We don't actually have that in Python. What we have are integer objects and string objects and special kinds of objects. So when we talk about strings in a couple days, we'll talk about that, because even Unicode, that a string in Python is actually incompatible with the standard Unicode data that we use on other machines. So if we have to communicate with another machine, and have a string, we have to turn it into Unicode. That's something we'll see either Wednesday or next Monday, somewhere in the string section. But everything in Python is an object, which means we can use those objects, have some built-in stuff about further things. We'll see objects later. It's more than just simple data. And there are methods and subsets of data inside of all our objects we can access. Numeric is a method, so we can check to see if a number or an input is a number, obviously, and then maybe cast it into an integer or a floating point number, and do that check before we do the casting. That way it doesn't just throw an error if it's something that can't be turned into a number. So that's a really useful one. And it has to do with strings, which we'll see more later. So if I run this, it's going to ask for a number. So I say 432, even though that came from the keyboard, so it wasn't the digits, it wasn't the number 432. It was, I'm gonna go back to the raw data thing. It was Unicode value, what is that? 53, 52, 51. So Unicode numbers are ASCII numbers. ASCII is the first 256 characters of Unicode. They didn't switch to a new system, they just extended it. But if I run that again and enter a string, so like give me a number, no, there's nothing numerical there, we get the false. So we have lots and lots and lots of built-in methods like that. There are a lot of those. I just thought I'd go ahead and show Numeric, because that's probably one of the most useful ones. Because when we get string, if we get input from a user, one of the things we probably want to do with that is, if we're expecting a number, we're going to do some math with it. And if it can't be turned into a number, that's going to cause a problem. So that gives us a way to check that. Lots of those built in. We'll see some more when we get to the string section. But there's built-in things. That's not the only thing we can check. I'm going to bring in a couple libraries. We saw the other day, there's the core Python language. Well, our keywords are what the interpreter knows. The interpreter knows things like what if means, what the equals means, what the x means. And then when we say Python language, we mean all the stuff built from that. So somebody already built up functions, pre-built a function called input that gets stuff from the keyboard and returns that so we can store it in a variable. Or functions like Numeric that we can use, or functions like print that sends things to the standard out for the system we're running on. So there's a lot of pre-built stuff. And not just that core kernel. When we downloaded Python, there's a huge, many folders of them. When you installed Python, on there would have been idle. Oops, that's not where I was going. On C drive. So quick place to get the address is if you open idle and the text editor in idle and go to save. Before you navigate anywhere else, it's going to try to save where Python's installed. So that's a quick way to learn where the language is installed or get the address. I've done it enough times, I know where it's at. My C drive, the users folder, the Chris user. There's a hidden folder, so you have to turn on all the hidden folders in order to get to it even. But in app data, there's a folder called local, and that has a folder called programming or programs. And in programs is a Python folder or a Spider folder, if for those using, because Spider uses its own installation of Python. And in that Python folder is a bunch more folders, including this one called library. There's our python.exe, that's the interpreter where the code actually runs. And there's a folder here called library. And hopefully that icon looks familiar. It's just the icon for Python scripts. So you'll see many, many folders just filled up with of Python scripts. And this is what we mean when we say language usually. The stuff that was pre-built. So let me open calendar. That's what I usually go for, just near the top. So we have some comments, some import statements. There's this list of things that we might need. A couple objects, we'll see those later. A couple more objects. Some variables. Oh, and then finally we get down to these pre-built methods. So we could import this library because it's not part of the kernel, the most basic parts that's always ever used. But we can import calendar because it is part of the Python programming language. And ask for this method is leap. And if we pass in here, it'll return true or false. So most of our things like that is kind of a standard to say the method returns a bool. But that's what the programming language is. We have lots and lots of those. And another one, the other two I put on the list here for today, that kind of be very useful, especially on Wednesday, we're going to get into strings. Yeah, this next textbook goes over strings and immediately into files, which I really like because the previous textbooks had like strings in chapter 3, and we didn't store those strings in a text file until chapter 11 or something. So when I saw that in this textbook, I was like, oh, what a great idea to put strings and text files in the same chapter. That way we can keep them around and store them. So that's what we get into starting Wednesday. But that means storage. So one that our book didn't mention is one of those libraries. I'm going to use the from notation. We have this library called OS. Import everything, the wildcard selector. And that's actually a folder. So inside of that folder is another folder called path. So we want something for both of them. This is something I use a lot. And whenever I do it, if we're OS is the library of functions to access and interact with the operating system we're on. So to interact with whatever operating system we're on, that's built into Python OS. And then inside that is this folder os.path. And we almost always need both of them. So I do this type of notation. You might remember we saw the other day import maybe the math library. And then if we needed something from it, we would type math, the library we're looking at, and then maybe the dot square root function. Something like that. If we use this other notation, I'll just stick that somewhere so it doesn't throw an error. We can also rename that as m, and then we do m dot square root. Is another way to import, or we can say from this library import and list out the ones we need. Or use the wildcard selector, the asterisk, this somewhat standard symbol that means everything, the fill in the blank symbol. And then when we do it that way, we don't have to say what library it's from. I do this quite often. We almost always need both of those libraries, and I always import it this way, so I don't remember which one the particular methods would be in. One particular method would be in, or but we might like to check things, not just check for numbers. That math library, we saw that the other day, so I'm going to try to strip this down to the most basic thing. So maybe we have something like here on my computer where I'm working at. I'm going to type it with slashes. So on a Windows machine, we use backslashes in our directories. And on a Mac, we use forward slashes in our directories. So typically in Python, we use the forward slashes and let it figure it out for the operating system. Because Python will know what's appropriate for the system that it's on. It's already built in. So on my folder, this directory I'm in, or where I'm working right now, the C drive, users folder, there's a Chris user,
We can't hear
Chris, I
you
think-
if you're talking.
or in other situations, we might need to know is this.
You were back for a minute, but we lost you again, I think.
Yeah, your mic keeps going in and out. Like you were out for a while. I thought it was like frozen.
Oh, sorry. Can you hear me now?
Yes.
Yeah, it came back.
Okay. Where was I when it went out? But I got this far, the is file. Did it go out again?
I think it was back where it was X.
Oh, so way back here. Okay, so let me go back a little. So one of the things that X could be is this string, which represents an address on my computer here. In particular, the file we're working on, right? So we could ask values about that in here with the built-in methods. So like in this case, is X a file? Which we know it is because I use the file I'm working on here. We run that to get the true, it is a file. Or is it a directory? Is third. Maybe we're looking for something. We're gonna dig through folders until we find the file we're looking for. And every time we find something, we need to know whether it's a directory so that we can start digging through looking for a file. So those are very useful ones. And there's lots and lots and lots of conditions built in like that. Usually things that start with is include that, but we'll see a couple more of those when we talk about strings and files starting on the next module. I just wanted to include them in the thing about selection structures. Does anybody have any questions about that? Hopefully fairly straightforward. Those other libraries have a lot of things built in. We can check more than simple comparisons with what's going on there. Because that sort of thing, those if-else statements like this, that usually comes fairly easy to people. Does everybody feel okay with that? I mean, obviously, there's, it takes a while to get used to the syntax of the language and just the logic of how a machine needs their instructions and stuff like that. Takes a little while to get used to that. But in general, does everybody feel okay, somewhat comfortable with the idea of how we put those conditions together? Are you guys here in the classroom? It does take practice though. This is a hard subject. Sometimes things are gonna come really easy. And those conditions are one that usually comes easy to people. And other things are gonna seem really, really hard. But that's why it pays a lot, which is probably why you all are here studying that in college, right? Easy things don't pay really, really well. Easy things don't pay nearly as much as what programming does. Sometimes, at times it will get difficult, but those conditions come naturally. And I had that list, I put it up here earlier, call it our 4 constructs. The tools we need to solve problems. Any problem. So since programmers, software developers solve problems, we need to study these tools. Sequential tool, some sort of order for things to happen in. We need the steps that we're going to carry out, the sequence of steps, which in programming languages, that's the order of the instructions we give to the machine. So that one's trivial in the programming language. That's the order we write our instructions in, or the order we lay our pictures out in if we're in a no-code or low-code solution. There are a lot of those, and then we let the computer type the code in the background, because computers never make typos. It's humans that make typos. Once we have an order, we might need to make some selections along the way, some sort of selection structure. The 4th one we just looked at, that's the invocation. I'll skip down here. That's showing the screen. The invocation structure, which is to jump out of our sequence and come back to it. So that's what a function is. So things like that pre-built is file thing we just checked on there on that Python example. We jumped out of our sequence, ran some code that was written in another Python script, and then came back to our sequence right where we left off. Invocation. And then the 4th tool, or actually the 3rd tool, I skipped over because the next one we're getting ready to talk about, is reiteration. We need a way to repeat things, repeat steps. Example I like to use, or there's a couple of them. First one I like to use is mowing the yard. You get behind your push mower, get that started up, and you mow a strip of the yard. And this is how I'll use these words. Repetition, repeat, and reiterate, I will use differently. So repeat, I will use that to mean the same steps. So with mowing a yard example, after you mow that strip, get your push mower and mow that strip again. And repeat, and mow that strip again. The same strip, exact repetition. Sometimes we want that in programming. The first example that springs to mind is like an animation loop on a website. Right? When somebody logs onto our website, we want that animation loop to start, and it's going to keep looping, showing them our animated logo until they leave our website. That is an exact repetition. So sometimes we do want the exact repeat, but usually we want a little bit of variance, and that's where I use reiterate. Repetition with variance. So with the mowing yard, our yard example, get behind our push mower, mow the strip. There's the end of the camera. Not too far. After mowing the strip, then we turn around and move over and mow the next strip. So our basic instruction is the same. We're reiterating that mow a strip instruction, but there's some variance. The turn around and move over that allows us to eventually solve that problem of getting the grass mowed. Which now is about the time we don't have to worry about that for 6 more months now. But that problem will come back around again. So we need ways to repeat things. And what machines have to repeat things is kind of difficult. So, let's see. That way, a little bit more of the board showing there, that'll work. So what machines can do to repeat things is something we've all experienced before. I assume everybody has experienced this in America before. So maybe we have somebody singing. Somebody sings into a microphone. That sound travels down a cable, gets amplified, and comes out louder than it went in. And depending on the situation, how things are set up, that sound coming out of the speaker could go right back into the microphone, down the cable, get amplified, come out a little bit louder than it went in. Nothing's moved, so it's, once again, it's gonna go back in the microphone, on the cable, get amplified. And before long, the room is just filled with this annoying big screeching sound, the audio feedback. Usually an annoyance. Though some musicians, the first two that always spring to my mind are Jimi Hendrix and Tom Morello, because they did it so well. They would use that feedback as just another note that their guitar would play. Jimi Hendrix mostly did it as little flares, accents on the notes. Tom Morello went a whole lot further and would use the feedback as the actual thing he was playing. He did entire song solos that are feedback and through effects pedals and things. But they did that very well. They learned to control that audio feedback loop. And that is what machines do naturally, a feedback loop. And feedback loop is simply, we have some input, some sort of processing. I'll just draw it like this. Our input feeds to something. That's still on the board camera, yeah. Then we have an output, and that output feeds back into the input. That's what we have in machines. Feedback loop. The output goes to the input. And audio example, the audio feedback is just an example within our modern society. I think everybody's experienced that. Both the really good ones or come across heard musicians actually use that in their thing. It makes a nice cadence at the end of a song sometimes, right? To just leave the instruments feeding back as the musicians leave the stage. It adds a lot of emotion to how that song, to the end of a song as well. So it's controlling it in order to use it. That's what machines have, but it can be really difficult to work with in programming. It's called recursion. I'm going to erase the picture. Output goes to input. That's what machines do. When we control it, it's called, for programming, we call it recursion. It's really difficult to work with, and sometimes we can't even solve the problem we're dealing with in recursion. We have to adjust our problem and modify it, and maybe even solve a different problem that can be translated into the solution to our problem. So it's really hard to work with. We will look at some simple examples of it when we've seen methods. Probably one simple example. And yeah, I'm not gonna spend a lot of time with it. It's hard to work with. So in a lot of our programming languages, there's a structure built in that is easier to work with, which is essentially the conditions like we just looked at. Our official unified modeling language symbol for a selection structure looks like this. The condition is a diamond shape. The international standard of pictures for communicating across language barriers. Selection structures, what we just finished talking about, those usually come a lot easier to people. It makes sense. We branch out one way or the other, a yes or no sort of thing. So since what machines have, the feedback loops, it's hard to work with. In a lot of our programming languages, they modified a selection structure so that one of our branches comes back around and we check that condition again. And that gives us a nice, easy way to work with it. Like if the selection structures made sense, the loops are essentially the same thing, but one of the branches of the path feeds back in to our condition to check again. And it's much easier to work with. A lot of our languages have that, but not all of our languages have loops. Luckily for us, Python is one that has loops. So we can work with loops in this course. I don't know why I rushed to erase that picture. I can go back to the screen share. So we have a couple kinds of loops. In SDEV 120, we talked about pre-test and post-test loops. That was the main one to learn. With Python, there's really two kinds of loops. And I'll just do them in an example here, because we're looking at Python now. And these two types of loops we have in pretty much all of our languages. So I'm just going to delete that stuff from earlier and start a new thing. So the first one is a while loop. So while counter is less than 10. So maybe we want to print something 10 times. Print something dash dash plus cast the counter in dash string. Sorry, it's been a long day, so I'm not feeling super creative, but we're just looking at the syntax here and a stripped down version of syntax. So once again, that general Python format, a keyword, the language knows, the interpreter knows, something unique to our situation, a colon, and then we indent everything that we want to happen afterwards. And then afterwards, we can reassign counter incrementing by 1. So just to make a keyword to make things happen repeatedly. While, and it's just like it's built from an if-else block, if block. So like we have while, if true, we do this stuff. So while true, we do this stuff. And for a while loop, we usually want to avoid infinite loops. If you do want an infinite loop explicitly, something like that one I mentioned a moment ago, an animation loop that just runs the whole time somebody's on your program or website or something. If that is what you want, don't be subtle about it. If an infinite loop is the goal, directly write while true so that any other programmer that looks at your code knows explicitly that was meant to be an infinite loop. But for us now, we'll just avoid that. I'll hit Control-Z a couple times and get back to this counter one. We don't want to go into an infinite loop, so we want to increment it. I'm gonna leave that increment off. I'll put it back in a second to show fixing it. So save that. Forgot to run that. Come over and we're getting this something dash dash 0. Our counter's never changing. We entered an infinite loop. On the command shell, so this will just loop as long as the computer's on. If that happens in Windows command prompt or PowerShell or a bash shell or a Z shell, if you've updated your Mac, or most of our shells, Control-C is cancel. It's way down there at the bottom. Let's Scroll down. Oh, can't really scroll down. Maybe we'll make that smaller. It'll fit on there. There we go. A keyboard interrupt. It's Control C in pretty much all of our systems. So if you're in the terminal or shell or something, Control C for cancel. If you hit an infinite loop, that's something we usually want to avoid. So to avoid it, always want to, in a while loop, always want to make sure that your condition also shows up inside the loop. So whatever variables or functions are used in your condition, that stuff should also be in the loop somewhere. Like counter plus equals 3. We'll count up by 3. We don't necessarily have to count by 1. Oops. Go twice. There we go. 0, 3, 6, 9. I just repeated that instruction to print some stuff to the screen, then incremented the counter. Did those same instructions again. Print stuff to the screen, increment the counter. Print stuff to the screen, increment the counter. In most situations, obviously, something a lot more interesting than that example, but we're just looking at the syntax here. That's the idea. A while loop. So while this is true, keyword and unique to our situation, a colon, then we indent the stuff we want to happen over and over again. The other type of loop is, well, in Python, we have for loops in pretty much all our languages. And in Python, a for loop is actually a for each loop. So let me make a short list. Hopefully everybody remembers arrays or list from SDEV 120. So I'll call it ARR equals sum list 5, 2, 8, 9. A finite list, a countable list. It's iterable. And iterable means something we can walk through. There's 4 things there. So iterable means we can walk through those things one at a time. And that's what for loops in Python are. They're what we call for each loops in other languages. So like for item, that's a reference name. I just made that up to represent what's in the list. For item in that list I created, then we'll do something each time. And it's for each item in that list. Print next is plus cast item into a string. So we'll walk through this list one at a time. And every time we look at the next item, as we iterate to the next item or the next element in the list, we're going to call it item. And that's the main 2 types of loops we have. So if I run that, you see we get that, and then we just loop through each thing in there. Your textbook seems to really like this other thing. I'll go ahead and do it. I'm gonna add some white space because I don't like typing at the bottom of the screen. Come up here. So for I in another thing, I use the word countable, and you've probably never encountered, let me stop the screen share. Whoops, stop share. Everybody's seen that symbol before, right? Infinity. Basically means more. Fancy way of saying more, no matter how big we get, is more. But the first place we learn infinity is with our counting numbers. 1, 2, 3, 4, and on and on and on. we could just keep counting forever. That's what infinity means, right? But that's not the only type of infinity. There's also an infinite number of numbers between 0 and 1. Right? All those fractional numbers, irrational numbers, and rational numbers, transcendental numbers, everything between 0 and 1, there's an infinite amount of numbers there. There's actually more here, a continuum. So that continuum of all those numbers between 0 and 1, that is bigger than our countable infinity. And I said it that way to bring that up. So if we wanted to iterate everything between 0 and 1, we can, that is not countable. But this type of infinity, just our counting numbers, 1, 2, 3, and so on forever, that is countable. So it's based off counting numbers. So that's what's meant by iterable. Countable, it's things we can iterate through. And even though we'll never count to infinity, the whole number infinity, there is a countable infinity and a non-countable infinity. There's different versions. There's more than one infinity, basically. So for our numbers, we could just pull up a list of numbers. And I threw some random numbers in an array there. But maybe we just wanted to do our counting numbers right in order, right? 1, 2, 3, 4, 5, 6. Neil's textbook really seems to like this. There's been times whenever I forgot it in this class and had to come back and talk about it later, because for the first 12 or 14 years I used Python, this was not there. We didn't have this function. It took a lot of extra work to get those numbers. But there is this pre-built method called range. Oh, and there's the predictive text. It needs those things. Like a little help menu pops up. So the range needs where we start at, where we stop at, and our step values. And stop, notice how start and step are in square brackets there in the predictive text. Those are optional. So we just said range of 20, print I. Let's keep it simple. We'll just print those numbers out so that there's an implied start to our countable numbers. So the endpoint is required. The start point is kind of trivial. So we say stop at 20. Stop screen share. This is a good place to express that start at 0 thing that shows up in programming. It seems different than like what I wrote here on the board where we start at 1 for the countable infinity numbers. Start at 20, if we think back about what 20 means to a computer, what is that in binary? Well, I'll do 8 bits. I don't have any 128s. I'm not going to have any 64s or 32s. A 16 will fit, which leaves us 4. So we won't have any 8s, a 4, and don't have anything else. So that is 20. That is 20 as an 8-bit integer. And we'll need all 8 bits to represent, or otherwise it wouldn't be an 8-bit integer. So we said stop at 20. If we said start at 20, here's where 20 starts, right? But we don't actually count 20 until we get all of that data in. End of data, meaning, sorry, I'll write that bigger. End of data, meaning 20 is way over here. So that's why that list on my screen only went 0 through 19. Because we start at the beginning, but we count at the end. So when we say go until 20, it's just going along, and then it's like, oh, wait, here's where 20 starts. So I went up until 20. So that's that discrepancy that since when we're little kids, we learn to start counting at 1, and then we throw in 0 later. And when we get back to computer programming, we start counting to 0 because we start at the beginning and we don't have that number till we get all those bits added. A subtle point, but it may make a difference somewhere in some problem that you're solving. So I wanted to make sure and take a moment to express it clearly. This range function that was just added a couple years ago, like I almost never think about it because, yeah, for the first 12 or 14 years, I used Python. I can't even remember when I first started using it. I remember which computer it was on, and I had it for a couple years. So I can't quite pinpoint the date of it. The first 12 or 14 years I knew Python, this wasn't available. That came later. Then those other things we could say where to start at. So maybe we don't want to start at 0. We want to start at 13. We're going to count teenagers in our neighborhood or something, ages 13 to 20, and feed in a different start point. Then we get those right in order, and then the step is the step size. Let's count from 13 to 200, going up by 43. I just kind of chose that randomly instead of stepping by 1, which that's going to be our normal, most common one probably. Step by 1, but we can put any number we want. We're going to start at 13, count until we reach 200, until we reach the beginning of 200. So we're going to stop at 199 and count by 43 each time. So come over here and run that. You can see it's going up, and then once we hit 185, adding 43 gets us past the start of the next bit of data. To express that point one more time. So that's kind of our options for loops. Most people find them very, very easy to work with because they're based off the selection structures, which are more intuitive to humans than recursion. We will see probably one example in recursion because it's hard. So we'll do a simple example, but not much because it's hard. And there's an easier one built into Python, and a lot of our programming languages have this, but not all of them. But that's kind of what we have to work with loops, the while loops and the for loops. That's our basic syntax for it. You all have studied logic and what to do with loops in SDEV 120. There's some more content on our textbook about it in syntax. Just think repeating steps. When steps need to happen repeatedly, that's where loops going. Very similar steps that we can just adjust slightly every time. And these are our main 3 options in Python. So we have that range thing now, so we can do for some index in that range, or for all the numbers in that range. But a for loop is really a for each loop. So for each item in this list we have, or anything iterable, a file. Earlier we saw that is file in this directory. So we can do things for like for each file in a list of directory listing. The method is list dir. So like that'll look something like a for file in list dir. We'd have to import the library, add some other stuff, but we can anything that we can iterate through. Lines in a text file. We'll see that on Wednesday or Monday. Whenever there's a bunch of stuff to talk about with strings. But does the basic syntax for loops there make sense? Because once you see that syntax, it comes down to just practice. This is an active subject. We learn by doing. So in most cases, I want to try to make sure there's plenty of time to do stuff. Those who are in my afternoon class know that sometimes that doesn't work out. There's a lot of content to cover. That happened this afternoon. I did manage to get the program running again, not crashing automatically by 4:49. So still had a minute of class left, but for us now, there's what, an hour and 15 minutes left to actively practice this subject. Anybody have any questions about that? The stuff from tonight? Okay, I assume the questions, or sorry, not the question. I assume the silence means no questions. So why don't we split off for lag time for the rest of the evening? For our scheduled time, my plan is to be here till 9:50, but if everybody leaves, I will probably head back to Clarksville myself and make some coffee when I get home. And if I do that, it takes me about 10 minutes to get there. For those who live up the northern part of the state, our Ivy Tech here in Sellersburg, if we turn right out of the parking lot, which is that direction for where I'm at right now, if we turn right and don't merge into the next lane, we're on the interstate on that. So it's jump on the interstate, and I am 2 exits down, which is 5 miles down the interstate. Get off that exit, and it's a half mile to my house. So for that, that'll be the amount of time that I'm out of communication. If everybody leaves campus here, then it'll just be me and the security guard and the janitor. And they'll be sitting around waiting for me to leave so they can finish up for the day. So if everybody leaves, I'll go ahead. Otherwise, my plan is to stay here till 9:50. In case you have questions, Ivy Learn messages and text messages make noise on my phone, so I can immediately jump back on a Zoom call. Otherwise, I'm always available to help. Ask me anytime. This is a time that I know I will be sitting here by a computer ready to answer questions. Otherwise, I will see you all on Wednesday. Everybody have a great night.